Hello and welcome back. In this example, we're going to go ahead and design a column. So we have this column, and it's a W12 by 50, and we have a dead load of 60 kips and a life load of 80 kips. We want to know what is the capacity of this column. Regardless what the load is, we're going to calculate the capacity of the column, make sure the column, once we come up with that, then we can compare it. So first thing we do, we go into ASD table 1-1, get all the information that we need for a W12 by 50, which gross cross-sectional area, Rx, Ry, flange thickness, and the web thickness, and also the BF and D. And so let's go ahead and do our load both in load and resistance factor design and then an allowable stress design. Then we will continue. Again, for load and resistance factor design, the load combination for dead load and life load, the one that's going to give you the highest value, it's number 2. Okay, so our load comes out to 1.2 times 60 for dead load plus 1.6 for the life load, which was 80 kip. And that comes out to 200 kip. And for allowable stress design, we just add both number, which is 60 plus 80, and that's 140 kip. One of the first things we want to do is check for local buckling. Take a look what I have on a board here for local buckling. We worry about the especially in W shape. We have the flange and we have the web, and we want to know the width to thickness ratio. That is, which we call lambda, is gotta be less than lambda r. And if you take a look at the table B4-1, we're gonna go ahead and go through that check. First, we're gonna go ahead and do the check on a flange, which is the first first case. So we're going to have a B with the TF ratio, and our B. Now look at the table. Our B is W12. So the B that shows on the scenario 1 is half of the, basically this is a B right here. So which is basically 12 divided by 2. So we have 12 divided by 2, and flange thickness was 0.640, and that number comes out to 9.375. And this should be, hopefully, is less than 0.56 square root of E FOI. And that comes out basically 0.56 times 29,000 KSI divided by 50 KSI, and that number comes out to 1349. So that checks out. That means we're not going to have any local buckling for the flange. Let's go check for the web. For the web, it will be scenario number 5 on the table B41A, and we have a H divided by TW, and our H basically is from here to there. So you got to take that thickness, take this out, and that's called K. If you look at the, excuse me, look at the chart, and it's on table 1-1, I have it on a board, and our K comes out to 114. So this basically, H is going to be D, which is, this is D from here, minus 2 times K, and divide that by a TW, the thickness of the web. So I have D came out to 12.2 minus 2 times 114. Then divide by 0.37, and that comes out to, so this becomes 26.8, and hopefully that is less than, and that's scenario 1. The formula is given as 1.49 square root of E FOI And this is a standard number, which usually comes out to 3588, but let's do it anyway. 149 square root of 29,000 KSI. It's a modular elasticity of the steel. Divided that by 50 KSI steel. And so that's going to become 3588. So that checks out. This number is less than that. That means we do not have a local buckling issue. Now we're going to check for the effective length. Now remember, it's really important how the end of the column are supported for effective length, and that's kind of basically a column strength really depend on it. See what read what I have on the screen. So we're going to go ahead and look at the table is from table, this is all ACE of CA7, C-A7. We're going to find out that our Kx, which is equal KY, is equal 0.8 based on the fixed and pinned restrained end. So now, once we have that, we want to find out which axis is going to control. Basically, LC divided by R in the X direction, or LC divided by R in a Y direction. So now we're going to look at here. See, Y is a smaller. Therefore, this number is going to be larger. And we're going to say because this X is, Y is bigger, then that's going to control. So the bigger number going to control in here, LC over R in the Y direction is bigger than LC over RX. And we're going to go ahead and calculate this one. Therefore, we're going to come out to become KL divided by RY. And our K came out to be 0.8. And our L is 25 feet. Let's make that to an inch. Multiply by 12 and divide that by RY. And RY in this case was 196. And that will give me 122.45. Okay, from here on, now we have this number. There's two different ways we can calculate the critical stress. So one way is from the ASCE. Let me write this down. From ASCE table 414. And you can see it on the screen. And then we have to go ahead and interpolate between those two number and figure out the phi time FCR. And phi FCR divided by, for both for allowable stress design and for LRFD. So we're going to have a phi FCR by interpolation. And if you know how to do interpolation, I got a link down in my video. Go ahead and watch one of my video how to do linear interpolation. So I'm not going to waste time here. So phi time FR become 1507 KSI. And then we had critical stress divided by omega. Nice looking omega. That comes out to 1003 KSI. Later on, we're going to go ahead and calculate this using the equation E3. So I'm going to come back up here. I'm going to say, okay, now I have these. I'm going to find out the capacity of my column. So I'm going to go phi time Pn, which is equal phi basically time FSCR and multiply by the gross cross-sectional area. And we already have this, which came out to be 1507. 15.07 times the area. Area came out to be 14.6. And that comes out to become 220 kips. That is the capacity of my column. In this case, it happened to be more than the applied load, which that's exactly what we're looking for. So it's okay, it's going to check out. So now let's go ahead to do allowable stress design. In allowable stress design, we have the Pn divided by omega That's a good looking omega. So that's the same as a F critical time AG divided by omega, and that comes out to 10.03. We already have this number, came out 10.03, and time 14.6. So that comes out to 146.4 kip. And that is bigger than applied load, which is good. That's what we're looking for. Let's use another method to calculate these two numbers. I know we got it from the table, it's easy, but it's just for so you know this, and you should know this. We're going to use what I have on the board. Take a look at it. We're going to use the equation E3. So one thing we want to know first is 4.7. Let me make it right here. I want to know 4.7 multiplied by square root of E divided by f of y, and that give me 4.7 times 29,000 KSI, divide that by 50, which comes out to 113. Now we have that number. We would like to know our KLRY came out to 122. So if our number, according to equation E3, 1, so per E3 section, we find out that our KL divided by R is basically bigger than this number, and therefore we're going to use the equation E3-3, and that for it's going to be critical stress going to come out to 0.877 times F of E, and let's calculate F of E. So F of E, per formula we have right there, elastic buckling stress, is calculated by pi squared times E divided by KL divided by R and square it. So we know what pi is anyway, pi squared times 29,000 KSI, and divide that by 122.45 squared, and that came out to 1908. Okay, so now we have 19.08, and our F critical stress is going to come out to 0.887 multiply 1908, and that gives me 1674. We have found out the critical stress found out. I'm going to go ahead and calculate that. So it's going to be phi FCR AG, I got 0.9, and then FCR came out to 1674, I mean, multiplied by the area, 14.6, and that gives me 220, same thing. Checks out, same as the other one. And if I go ahead and do the same thing, FCR divided by omega, and that will give me 16.74, and omega was 1.67, and that will give me forgot to multiply by the area, multiply by 14.6, and that gave me 146.4. Checks out. So basically what we did here is we calculate the capacity of this column, which is a W12 by 50, is 25 feet long, is fixed at the bottom, pin at the top, the capacity of that column in that situation came out to 222 kips in load and resistance factor design and came out to 146.4 kip in allowable stress design. Two different ways. Using a table, which was a shortcut, quickly you got it, or you can calculate by hand, came out the same way. Now, so this capacity you have for this column, it better be more than your applied load. So the load we had in mind was 60 kips, and that load and 80 kips of live load, which comes out to 200, is less than this, we check out. I hope you like this. If you do, give me a thumbs up.